will start by thanking the organizer for giving me this opportunity to talk about my latest overview about what we know about spin and polarization of particles within hydrodynamics. The main parts of this presentation will be a general introduction to the topic, with a special emphasis on what do we do in hydrodynamics and how do we connect this with the observables we measure in experiments. Then, especially because yesterday I see there were some questions about hydrodynamics, if it is with a symmetric or non-symmetric spin energy momentum tensor. This is related to the spin tensor, and I will show why the spin tensor has been considered as something to add to the regular hydrodynamics to deal with hydrodynamics degrees of freedom. And I will focus mostly on the hydrodynamic freeze-out version of the picture, but something linking them is the Wigner distribution as a generalization of the distribution function in kinetic theory, in the relativistic Boltzmann equation. So I will mention other topics. So at first, at the theoretical level, we already knew for some time that there is a link between rotating states and polarization of particles. I'm putting here rotation in this way because if one has global equilibrium, there is one only pseudo vector in the state of the system, which is a Lagrange multiplier to have a non-vanishing average angular momentum. So every pseudo vector or rank 2 antisymmetric tensor has to be proportional to this pseudo vector, at least in the small angular velocity limit. I will not touch the topic of local equilibrium and which one is the best local equilibrium version of kinematics with spin, because there are, during these 2 weeks, there are many other presentations with fresh results about that. And I will not talk about which one is the best tensor if the vorticity, the thermal vorticity, and the other one, and the T vorticity. It's an interesting subject, but I will focus more on our current understanding and how to improve hydrodynamics to deal with it at the dynamical level to see if the system goes to equilibrium for the spin degrees of freedom at the same rate at which it goes for the energy and momentum. Now, the most important thing is to have clear the picture that when we do theoretical calculations, we deal with space-time densities. For instance, the energy density and momentum density, which is embedded in the stress energy tensor. It is understood through the correspondence principle as the expectation value of the corresponding operator through the state of the system here is rho. In general, the operator will be renormalized to have finite quantities. And in hydrodynamics, for instance, at least one tries to solve the evolution of this T mu nu, and then one can add other conserved charges like the barrier current or the electric current in the isospin too, if we ignore weak interactions. However, these densities on volumes of the order of the Fermi cube, they are not accessible from experiment, from direct measuring. What we measure is the particles that goes to the detector. So it is the spectra of particles and the spectra of antiparticles. And because of the way experimentalists have to reconstruct particles, in some cases like the lambda particles that decays weakly, violating parity, one can tell about the average polarization of particle given an antiparticle giving a momentum. And if we exclude polarization effects, usually we deal with that through relativistic kinetic theory. Relativistic kinetic theory is the covariant version, relativistic version of the Boltzmann equation. So the momentum projector of the space gradient of the distribution function is given by the collisional kernel. And after the freeze out, when the collisions are zero, one has only free streaming of particles. And free streaming can be easily dealt with. From hydrodynamics, one can have the tensor T mu nu, for instance, and there is a correspondence between T mu nu within hydrodynamics and within kinetic theory. So what one can extract the distribution function, which is a probability density in phase space and momentum. And through that, making a space integral of the distribution function at some time later after the freeze out, one can get the spectra. Now, one can see already here, the main problem with this kinetic approach is that usually the polarization of particle is introduced only as a degeneracy factor. S is the spin of particles. So each polarization state is considered somewhat like an independent type of particle that evolves with the other. The biggest problem is that, yes, this is assuming that polarization states are equally occupied, but one could have different answers, but kinetic theory in its most basic formulation doesn't give us any suggestion how to deal properly with polarization degrees of freedom and how to connect space-time density measure with spectra and polarization. Only with the spectra. Now the most immediate question would be, why not using quantum field theory? Because by its very nature from the start, a spinor field has 4 components. It has embedded the information about the polarization of particles, and all of the tensor, including the T mu nu and the electric current, the baryon current, will have by the very start some information about the polarization states. Unfortunately, now I wrote the current because it's a smaller formula to write on a presentation, but it's still rather uneasy to look at. Unfortunately, the expectation value of the baryon current is not in a form similar to that of kinetic theory. There is not a phase space density. It is just a factor, an exponential factor with the position, and then there are the expectation values of the creation and destruction operator. I highlighted in the first row the particle contribution, the antiparticle contribution, but there are even two terms which are mixed in particles and antiparticles. And if the quantum state of the system is not an eigenstate of the number operator, this object here, these expectation values here are not zero, and they are important to maintain the divergence free of the current. Sometimes I've seen people confused because there are two momenta here, P and P prime. And some people think that it is something related to scattering, but I would like to remember that at this level, I'm only talking about free fields, so that the renormalization is just a normal ordering. So every scattering is trivial. It's just that the tensor and the expectation, the curve vector and the expectation value of the operator, they are just bilinear and they depend on two momenta. Looking at the explicit space-time dependency, one can see that just making a volume integral, these exponential factors become simple Dirac deltas in P plus P prime or P minus P prime. Now, one from codes and calculation have the T mu nu and J mu only up to the freeze out, but we can use an application of the Gauss-Green formula with the divergence theorem to obtain the values to show that the volume integrals are the same as the freeze out hypersurface flux, and that has some simple operating condition, which is the system is isolated. So let's say that we have this shadowed area, which is a flux tube. In this shadow area, I assume everything is during the after the freeze out, so we can approximate every field with free fields. There are no interaction, but there will be a flux tube. And as an isolated system, nothing will enter the light cone, the forward Potnier light cone in which the flux tube is included. And because of causality, with a little abuse of notation, we can say that observables and Hermitian operator fluxes cannot cross the light cone. In this way, if one takes this space-time region in the dotted lines and take the divergence of a conserved current, can apply the divergence theorem, so the only non-zero remaining parts will be the volume integral at fixed time will be equal to the flux on the freeze-out hypersurface. That can be as complicated as one can think of. So we can take the volume integrals, and we have now something which is easier to understand. First of all, the creation and destruction operator. Regarding the creation and destruction operator, only the diagonal terms remain, so with the same momenta. And there is a clear distinction between particle and antiparticle contribution. So one sees that, yes, by having a volume integration, we lost some information with respect to the vector and tensor densities, but we can see that natively, without approximation, quantum field theory, giving some T mu nu and J, will have a constraint on the possible spectra of particles because of the charge imbalance regarding the conserved charge. And for energy and momentum, there is the shape of the momentum spectra, which is constrained by these conserved charges. Now, these combinations here can be shown exactly to be related to the spectra if one uses the principle of quantum mechanics. I've seen that some people are not very familiar with it, so I'm just quickly skipping over, quickly showing these. The invariant particle spectra is indeed 1 over 2 pi cube. The 2 pi cube should contain an h bar if somebody wants to put back dimensionful, if someone doesn't want to use the natural units, and they're here because of the normalization of the fields. Indeed, in a generic quantum system, being drawn the state of the system, one has the possible quantum state of the fields, psi i's. These embed all the quantum fluctuation, superposition, diffraction, and everything. And then there can be a residual probability, which is this serif P, which is a classical probability to be in a quantum state rather than another. These probabilities, they are classical probabilities, so they are limited between 0 and 1. And the other one, and the most important part is here, the quantum state and the wave function. The quantum state can be generically written in this way. The vector here is a vector of n particle of momenta p. This underline means that there are n particles, so it's not just 1 3 momenta, it's n 3 momenta, and at the same time there is the polarization state, the same for the antiparticle, and this alpha n bar is a partial wave of the wave function with a number of particle and antiparticle which is fixed. And the integral here is just a shorthand notation for the covariant measure. Again, the two here, instead of the more familiar division by the energy only used in kinetic theory, is just because of I'm using the standard normalization of the fields used, which one can find in the Peskin-Schroeder, for instance. So after some calculation, if one is familiar with the concept of the one particle reduced density matrix, the expectation value over a quantum state of a dagger p prime is the one particle reduced matrix times the average number of particles. Using the standard orthogonalization relation between the quantum state, one finds that this object is just a division by the square root of the two energies. And then there is an integral of all particles except the jth one. So all the k's except the jth one are integrated on, and the jth part of the wave function is just with p, while in the complex conjugate, while it's p prime in the other part of the wave function. In particular, because of the normalization of the wave function, if one has a trace of these and an integral in the momentum, one obtains the average number of particles. So the physical interpretation of these is that this expectation value is just the average number of particles times the probability density to find a particle in a momentum state and a particular polarization state. Okay. So we have seen that these objects are just the spectra, the invariant spectra, and there is a problem that there is a direct sum of the polarization states, and neither the electric charge or the energy and momentum are sensitive to the polarization state. So any possible answers is somebody wants to directly go from hydrodynamics to a freeze out. Any possible answer is including unphysical ones, like every particle is spin up, would pass this check. So it is possible to take the stress energy tensor and obtain some information about the polarization, but it's not so trivial. And that's why I'm talking about a little bit about the conserved current. Now, the stress energy tensor in gravitational physics is usually the derivative of the action of matter with respect to the metric tensor. This is clearly the source of the gravitational big G, G mu nu. But the fact that this is corresponding to a conserved energy and momentum is not obvious. And indeed, in quantum field theories, one uses typically the Noether theorem. The Noether theorem states that for any symmetry of this kind that leaves the action unchanged, so the position will change and become this psi mu, and the fields, in case we have spinors or tensor, they will change too. Then one can obtain a conserved current. So the divergence of Q mu in general is 0. One obtains this by sending this epsilon to 0 in order to have infinitesimal transformations. And the conserved charge is just the volume integral of Q0. For instance, if somebody has space-time translation, delta x mu is just a constant, and the fields do not change. Both spinor and tensor fields do not change under translation. So one has the canonical stress energy tensor that in the case of a classical Fermi field has this form. However, one can see already that this form is not symmetric like the gravitational one. And with respect to transformation of the proper orthochronous Lorentz group, one has an infinitesimal omega mu nu, which is a rank 2 antisymmetric tensor, which embeds both rotations and boosts at the infinitesimal level. And then there is the global change of the fields, which will be this omega mu nu times the particular representation, which here I wrote sigma mu nu, that the fields are in. So from the invariance under the Lorentz group, one has the angular momentum flux, which is a divergence-free object with respect to divergence to the first index. Lambda is antisymmetric in the last two. And one can recognize the canonical stress energy tensor in one part, and then there is an extra part. The extra part is called the spin tensor, which has this form for the Dirac fields. It can be proven that this tensor is actually totally antisymmetric under the exchange of all the indices. However, in general, the spin tensor is antisymmetric only in the exchange of the two indices after the comma. Now, this tensor, the spin tensor and the stress energy tensor are not uniquely defined because there are two ways to change the currents but leave the conserved charges invariant. One is directly changing the action. For instance, de Groot in his book, Passing from Quantum Field Theory to Relativistic Kinetic Theory, he doesn't use the usual scalar action, but he uses a different action, including second order derivatives. And that's already enough to change the tensor. But there is another change, which is often called pseudo-gauge transformation, which is completely defined by these two tensor, a rank 3 tensor G and a big psi, which is a rank 4 tensor. G is antisymmetric in mu nu because it has to be a spin tensor, which is antisymmetric, while this big psi is antisymmetric in both the first two indices and the last two. By construction, the total angular momentum is not changed. And I'm not talking much about this because the author of this paper are here at this conference, so they will talk about this transformation and the physical implication of those. However, for our purposes, we can say that a particular case is the Bell-Infante transformation, in which the G tensor is just the canonical spin tensor and the Xi tensor is vanishing. So one remain with a symmetrized tensor, and usually people just ignore the antisymmetric part and just say, then we have the symmetrized tensor, which is equal to the gravitational one, and both the total momentum and the total angular momentum are given by that. It looks like that regarding the currents for the energy, momentum, and angular momentum, one lost 6 equations, but it's not really like this. If one sees that the Bell-Infante tensor, it is not manifestly symmetric, because there is this part here, the gamma matrices and the derivative is not symmetric by an exchange, and this term here is a divergence of a totally antisymmetric tensor. In order to show that this is indeed a symmetrized tensor, one has to do 2 things. Either solve directly for the fields, which is usually not done in hydrodynamics, or keeps the fact that the antisymmetric part of the Bell-Infante tensor has to be vanishing, which is, again, it's a set of non-trivial equations regarding the fields that are connected with T mu nu, the symmetric part. So it's not, this part has not been undertaken, but it can give some constraint on the form of T mu nu and possibly of transport coefficients. Then the spin tensor is called like this because if one takes the conserved charge, now we pass to operators, so I put an overhead hat. If one has a Fermi field and takes the angular momentum, so the generator of rotation and boosts, and write it without the gamma zero simplifying it, one has that the first part, if it were something like a wave function of a quantum particle, it would like that this gradient here just takes some momentum, and this is just the external product of the position times the momentum weighted under the wave function, while this other term, which is coming directly from the spin tensor, it actually mixes the components. And the spin tensor is not conserved because only the total angular momentum tensor is conserved. So if one takes the volume, it's not an invariant. And we see that here there are 2 terms which are time dependent in general. But the other 2 terms, that depends on the spectrum. This time they don't have the same spin index and they have a non-trivial sandwich between the eigenvectors, the eigensolution U and V of particles and antiparticles. And it is directly sensitive to the polarization state. Sigma is just this object, which is the substantially a diagonal matrix with the Pauli matrices. It is not really true that in the case of quantum fields, this term here doesn't meet the spin components because these 4 component fields, they include this structure, which is momentum dependent on of the fields. And actually the time dependent part here is compensated when one looks at the total momentum or the total angular momentum of a Fermi field. So now we have seen that spin is related to angular momentum, to polarization. And I think it's useful to talk about the quantum relativistic generalization of the polarization of particles. because in ordinary quantum mechanics, one has just the wave function psi, one has a sandwich with the Pauli matrices and have the average polarization. But in relativistic physics, this is a 3-vector, it's not any longer okay. So the most straightforward version is to follow exactly the same steps which are used in classical physics to define something which is the polarization vector, which is the analogous of this sandwich between psi and the sigma matrices. In 4-dimension, one doesn't have the cross product, but one uses instead some antisymmetric tensor. This is the orbital part of a classical object angular momentum. And then one has an internal part. The internal part can be completely classic, like rotation of an extended object on itself. In particular, in the lab frame, one has that 1/2, they contracted with the 3-dimensional Levi-Civita symbol. One obtains again the classical form of total angular momentum. Then one extend these in the relativistic physics using the Pauli-Lubansky vector, which is a contraction of the 4-dimensional Levi-Civita symbol. And again, here there is a refuse, I didn't put a mass. The mass is needed for dimensional reasons. And the polarization vector in the comoving frame is equivalent to the internal angular momentum vector, but it is defined at the level of operators, even in quantum field theory. So one can check which one is the polarization of a single particle just by taking single particle states, which is this psi1. And one sees that the spin structure here between U and the sigma matrices is the same as the one seen before in the spin tensor. And then there is this wave function here, which is substituted in a multi-particle case by the expectation value of A dagger A with R and R prime spin indices. So in particular, one can take the space part of these, the 3 components, the 3 vector, and it's not immediate to see, but this term in the square parenthesis, it's actually equivalent to say that the polarization in the comoving frame is just this phi sigma phi. So in particular, this spin density matrix is just contracted with the 2-component spinos. It is equivalent to a 2-component classical particle. One needs to be in an eigenstate of momentum, so this wave function should be arbitrarily close to a Dirac delta on the 3 momentum in order to have a well-defined P to use the classical formula to go from the lab frame to the comoving frame. And now, we already said that relativistic kinetic theory has to be extended if we want to include polarization degrees of freedom. And one of the best way to do this is to use the Wigner functions, or better, to use an evolution of the Wigner function, because the Wigner function has been worked up originally for the wave function of single particle ordinary quantum mechanics. So one has the probability, which can be written as an integral in an external parameters times the...
Leonardo, sorry, you have 10 minutes left.
Yes. Where was I? The Dirac delta can be substituted by the integral representation of the Dirac delta, and with minimal assumption over the smoothness of the integral, one can exchange the P integral and the external parameter integral, and have the Wigner function, which is an attempt to have a quantum version of a phase distribution in quantum mechanics. In particular, the momentum integral is the probability in position space, and the position integral is the probability in momentum space. A very useful approach is to do the same, but with quantum field theory operators in 4 dimensions in order to have a weight, which is an operator, and of course the expectation value is the classical part, in both space and momentum-like variables. I call them K here because it's important to remember that these are not, in general, on-shell quantities. In particular, not all properties are retained because the wave function here imply that under a Gaussian smearing over the momentum and position of the Wigner function becomes non-negative. But if one uses the Wigner distribution for quantum fields, that doesn't apply anymore. In particular, if we take a scalar field, because it's simpler, just using the Klein-Gordon equation, one has this set of 2 equations. These 2 equations because W, the Wigner distribution, is defined as a real expectation value, so the purely imaginary part is an independent equation. And through an H-bar expansion, one can ignore this first term and say that the distribution must be on shell. If it is on shell, without any loss of generality, one can divide it in the positive frequency and negative frequency. So one comes back to something that really looks like, in an H-bar expansion, to the pre-streaming of particles and antiparticles. The only difference is that this distribution, they are not probabilities and they don't have to be positive. They can have some negative part, even if at global equilibrium, they are usually completely positive. Now, in order to talk about polarization, we need Fermion fields. The complication is that the Wigner distribution at the operator level is a matrix. A and B are indices of the spinor fields. And all Dirac bilinear can be obtained, all expectation values of Dirac bilinear can be obtained as a K integral of traces of this matrix with the Wigner distribution. Sometimes the definition is different. It's used a psi bar, but this definition is explicitly Hermitian, so we can use being Hermitian, we can use the Gauss theorem to transform flux over surfaces into purely spatial integrals. And this can be done because K times the Wigner distribution is exactly a conserved current. And in this way, this rather complicated formula becomes much easier. In particular, the trace of this invariant is just the invariant spectra. And more over that, if one has a trace with these matrices, one obtains exactly the polarization of particles. One obtains the invariant spectra that can be obtained through another trace times the average polarization. So the Wigner function itself is all we need to extract polarization information from space-time density of tensor. As a final note, it could be interesting to see that this particular integral corresponds to the flux of a rank 2 tensor, which is manifestly conserved, and it's directly linked to the polarization because the conserved charge is the sum of the polarization of particles minus the sum of the polarization of antiparticles. Because in a non-interacting theory, the polarization at the level of expectation value of A dagger A is invariant because A dagger A, they do not depend on time. So. In conclusion, relativistic kinetic theory must be generalized to take into account spin degrees of freedom. The Wigner distribution can be used to translate space-time densities of tensor into spectra and average polarization of spectra. It can be used directly if one tries to solve that with an extended kinetic theory approach. It can be used directly to compute the evolution of the fireball, or it can be used to extract some improved version of hydrodynamics that takes into account spin dynamical degrees of freedom. And I'm finished, thank you.
Okay, thank you for this general talk. And I would like then to open so there is much time for questions. So I saw raised hands, and I would like to especially to encourage people to ask questions, especially the young, especially younger people that I cannot see by face, but please do ask questions now and over the roundtable discussion later. So I can see raised hands, and I think the first raised hand was by Chung. So please.
Yes. Would you please go to the definition of the Wigner function for Fermion by Spinner? I think 2 slides before. No, I cannot see it. Maybe.
This is the definition of the Wigner function through Spinner.
No, this is by Spinner. Yeah, this one. So my question is that, you know, normally we use a psi bar psi. So you use a psi dagger psi. So what's the difference?
It's just a matter of convention. Just like the fact that VAB here on the left correspond to psi B and A. There is both the convention with the opposite indices. Sometimes there is a minus or a.
No. My question is you use psi dagger, and
yes, because it's Hermitian.
We use psi bar. Psi bar is a psi dagger gamma 0.
Yes, I use psi dagger because in this case the operator W is Hermitian. But it's not important because if you see here, there is always a gamma 0 in the traces. If one puts the gamma 0 here, remember that the B component is here on the left, then it becomes automatically a psi bar. Many times it is used psi bar and psi because direct bilinears, they are defined as psi bar, psi, and it is manifestly covariant at the relativistic level to have just Lorenz indices. Instead, in this formula, there is a gamma 0. But in order to use the Gauss relation properly, I think it's at least necessary to have a Hermitian operator, which if one uses psi bar and psi, W is not Hermitian and not observable, at least not manifestly observable.
Okay, I think.
Okay, yeah.
We can move to the next question by Kenji, please.
Yes, thank you very much for a very nice summary. And so your talk is very much focused on the fermionic sector. And my question is, if one wants to apply this kind of formalism to the whole evolution of the partonic degrees of freedom, of course, the gluons, or generally speaking, the gauge fields must be included. And so to me, it is very non-trivial how to apply this kind of description for gauge particles.
There are some works that I didn't cite here because I tried to keep this explanation in the most simple and non-technical way, but gauge fields that they need a gauge, I mean, not only gauge, if there are gauge fields, first of all, that you need a gauge link between psi and psi bar, even for the fermions. Otherwise, we have non-gauge invariance objects. And then, yes, the gauge fields are more complicated than this form. At least the Wigner function I've seen for gauge fields, like in the Heinz paper in the 80s, are more complicated.
And my question, what I really want to ask is more specific. That is, for fermions, the polarization takes a gauge invariant form, like as you showed, gamma I, gamma 5, but in the case of the gauge field, it seems to be a gauge dependent, and so this looks like not really the physical observable. So do you have any idea to define the polarization in the gauge invariant way? That is actually my question.
Actually, just if I understand the question correctly, 1 second, I'm just messing up. I'm trying to get to the right page, 1 second. I don't know of any people that actually did polarization studies on gauge bosons. And gauge bosons, of course, the Wigner function made through the vector potential, they are not observable because the vector potential is not observable by itself, but only up to a gauge transformation. Here. However, this approach using the Pauli-Lubansky vector divided by the mass substantially, and the physical states for gauge fields, so instead of psi1 for fermions, one could put, again, they have to be the physical states for instance, the electromagnetic fields, because not all polarization are physical, but it should give some answer. However, how to connect this with the Wigner function of gauge boson, it could be a non-trivial problem, and I completely agree with that.
Okay, thank you very much.
Okay, so let's move to the next question. Masood?
Okay, thanks. I have a general question, and that is, since the Wigner formalism in quantum mechanics is supposed to be equivalent to the Heisenberg and Schrödinger picture, can we say that the Wigner formalism in equilibrium is must be equivalent to thermal field theory?
I'm not sure that I understand the question here.
Okay, let's assume that we find a quantity, we calculate the quantity from Wigner formalism, and we also find the same quantity from thermal field theory, and if they are, they should be identical, yeah?
Yes, of course. If I understand well.
Okay, thanks.
If I understand well, the point is that whatever you can, if you see this first part of the trace, these expectation values, so this is bilinear field, can be obtained through the Wigner distribution. If one were able to solve exactly the Wigner distribution, then yes, it would be solving exactly quantum field theory.
So at least if
which
we
can
found
be
that,
done. I mean, at the global equilibrium, it can be done. The Wigner
yeah, okay.
function can be
Exactly. I mean that because
the global equilibrium.
the thermal theory is at equilibrium. Yeah.
Yes.
Okay.
Depends
Thanks.
which equilibrium, but grand canonical equilibrium. And the next talk will be about exact solution of the Wigner function, as far as I understand. So,
yeah, I think the question is, so this Wigner function is general enough to be calculated with any density operator. So it is not necessarily at equilibrium.
Yeah, but quantum field theory is, the thermal field theory is based on just only in equilibrium.
Well, this is in a sense a statistical field theory, so not
Okay.
necessarily at equilibrium.
Okay, thanks.
Rajiv Singh. So next question.
Yes, I have two naive questions. Sorry. So can you please go to the page number 20?
20.
Yes. So in the last, yeah.
Overshoot.
Yeah. So in the last equation, we have done normal ordering of two operators separately, not, I mean, together. Why?
Yes, because, okay, you cannot see it here, but okay, how to say? The normal operation is in order to have always single particle expectation values.
Mm-hmm.
I mean, if you have a normal ordering of two operators, so you have a dagger, a single particle observable has zero expectation value with that.
Okay.
Because there is only one creation operator in the state. So with two destruction, it will go to zero. On the other hand, if you have a dagger A is just the square of an operator, of a number operator. If there is one particle only, you can have it. This is rather general when you multiply operator. Mm-hmm. They should be renormalized if somebody has a quantum field theory. Mm-hmm. Because they are the generator of the Poincaré group. And they should be renormalized.
Yeah, and second question is on your page 25. Yeah, so this WXK Wigner function, after doing this D4V integral, P and Q are on the mass shell, but what about their combinations, like P plus Q and P minus Q?
They are on the mass shell and the same mass shell. So P minus Q is never on shell.
Okay, and P plus Q will be on shell only if P is equals to Q.
No, I'm sorry, I said something incorrect. In general, they are not on shell, but when they have the same sign, it is something like P is equal to Q, mm-hmm. P plus Q half is mm-hmm. just P, and it remains on shell.
Okay, and here
because if one performs this V integration first, one ends up with K on a 4-dimensional Dirac delta, which is K plus minus 1/2 P plus Q half, or P plus minus Q half. Mm. And the only one that can be on shell with the same mass shell is P plus Q when P is equal to Q.
Okay, and here K is not it's like a wave number vector, right?
Yes, K is a wave number because it's not really, it's a parameter, it's an external parameter actually. It's not related directly to the momenta of eigenstate of the Dirac equation. It is in some cases, like grand canonical equilibrium, but it's not always.
Sorry, Leonardo, there are two more questions. I think that this is an interesting discussion that we can continue in the roundtable time. I would like to ask Oleg to ask his question.
Okay, thanks. And I have probably a short comment and a question related to Kenji question. And really the extraction, somehow separation of gauge field angular momentum to spin and orbital part, it's a problem. And it's extensively discussed for gluons in proton, for example. And here, in relocalization, in some trading between orbital and spin angular momenta, the key role is played by boundary terms. And for example, for hadrons, this analysis of these boundary terms leads to some constraints for axial current matrix element, and there is a hint that this is not possible to similar matrix element of gluons. So my question is, what about boundary terms in hydrodynamics?
What about? Sorry, I didn't hear the very last words.
Boundary terms, because the problem, the procedure of applying Belinfante transformation, of relocalization, then spin is written in orbital form.
You mean about the pseudo gauge transformations?
Exactly. And I mean the boundary term, because there are some constraints for boundary terms. And for example, for hadrons, these constraints are quite useful. They provide some extra.
You mean something like the meat-bug model?
Well, it's actually I analyzed something in a more general context. Like I may send the reference. It shows that, for example, there are no poles in singlet axial current matrix elements, and I wonder maybe similar constraints may appear also in hydro. I would expect that something like that may appear, but my question is it first, maybe two parts. First, is it something already just analyzed? Maybe there are some reasons to disregard, to discard these boundary terms. And second part, maybe it's possible to analyze them.
Well, at this, if I understand the question well, at this level of pseudo gauge transformation, usually people assume that all fields, they vanish close to the boundary. So the surface terms are zero. But it is true that, for instance, in a spherical bounded region, one cannot do this with spinor fields, because otherwise they trivials the field.
Maybe this is a particular, what you mentioned now, it
has been worked out. This particular problem, it has been dealt with, because even if the fields are not going to zero on the boundary, if these currents have a vanishing flux on the boundary, you can still have pseudo gauges like these ones. If they are not going to zero, of course, you cannot apply these. But I don't think there is something like somebody that proposed one tensor that should be, because of experiment, the correct one, because there is some boundary that do not accept any other one.
Let me remind everyone that there will be more talks about the subject later in the week and the next week. So I think it's a very interesting topic, but maybe the discussion becomes long, then we can move it to the roundtable discussion today or later in the week. So let me ask Giorgio to ask last question.
Yes, it's a fast question and comment and a plea. The plea to everyone working on this is to please stop saying that you're expanding around h bar. H bar equals 1. I think, please correct me if I'm wrong, but what you're saying when you're expanding around h bar is you're expanding around where a semi-classical limit where the one particle Wigner function is enough. The Wigner function is not like a density matrix in the sense that it doesn't capture the whole Fock space. You have a 1 particle, 2 particle, 3 particle, blah, blah, blah Wigner function. And
you're referring to this slide, right?
well, yeah, I mean, you said exactly. And you're expanding around. I mean, there is an expansion parameter. It's basically the occupation number, I think. I mean, please correct me if I'm wrong. It's basically the occupation number where you can use one particle Wigner function and truncate it at two particle or something like this. And I think this is an important point to make. I mean, for example, to answer Kenji's question, such an expansion doesn't commute with gauge theory. Occupation numbers for polarizations of vector mesons are badly defined, and I think this is the source of some of the confusion here, in my opinion.
However,
please correct me if I'm wrong.
Maybe I wasn't clear, but this H-bar expansion is only to show that in some limits, the Wigner distribution becomes something very close, or possibly exactly the distribution function for free streaming. And the book cited here is actually considered only the case of non-quantum physics. So one starts from quantum field theory, then goes to classical physics, and it does think about the lowest order expansion. But I agree with polarization of particle or spin 1 alpha H bar. We cannot say that 1 alpha H bar is much larger than H bar when you look at the particle polarization. So, however, the rest of this is just to show what happens, but the rest of the talk was without assuming any expansion in H bar at all.
Fair enough. Okay, fair enough. The limit in which quantum physics becomes classical physics is large occupation number, right? I mean.
Okay, so I would like. Okay, so I think we are. I would like to make a comment and a question to Leonardo, to confirmation to Leonardo. So, as far as I understand, so one of the messages of your talk is that the expression of the polarization vector is independent of the pseudo gauge, because you get it with a Wigner, right?
Yeah, maybe I was too hasty because I was planning to say that explicitly. The polarization vector depends on the global conserved charges.
Okay, so that means
it doesn't depend on pseudo gauges.
It does not depend. The expression
does not depend on pseudo gauge here. It does not depend on pseudo gauge and the choice of stress energy tensor, spin tensor at this level, and it doesn't depend on it even at the final formulas.
Okay, so this is, I think, a point to make.
Okay, Francesco, we have the paper with Benck-Freeman, 3 years ago about this, unless you use, Bell-Infante spin tensor, this is 0, so you cannot get the polarization from this.
So sorry, I didn't get. So do you agree or do you disagree with?
Yes, I agree, but we wrote the paper about this 3 years ago with Benck-Freeman, That's,
okay, no, I mean, I'm not questioning priority. I'm just saying that.
Yeah, with the same point somehow.
Yeah. So I think that so let's. I would like to thank Leonardo again for the presentation.